For this project, I'm going to be talking about the UART receiver that is on the Go board. Just a reminder that you can still purchase the Go board if you haven't. Just go to nandland.com and place an order today. So first of all, let's talk about, well, what is a UART? UART stands for Universal Asynchronous Receiver Transmitter. So universal means it can be used in a lot of places. Asynchronous is a word that we've come across before, but just to remind you guys, anything that is asynchronous means that it does not have a clock. So synchronous design means that it is clocked. Asynchronous means not clocked. So there's no clock involved, which is kind of a nice feature of the UART. It's just one line, one data path. Sometimes you can send a clock and data, but this one just has data. And receiver/transmitter. Now originally when I created this project, I was going to be doing the receiver and transmitter together in one project, but I decided that it was a little bit too much to bite off for one YouTube video and one project, so I broke it up. So part one is going to be taking data from the computer. The computer is going to be transmitting it. This is a buffer. This is what this triangle represents, is some sort of driver. And we're going to be driving the data onto this single wire here. And the Go board is going to be receiving the serial data stream and doing something with it. Part two is going to be basically the exact opposite, where we're going to be transmitting data from the Go board back to the computer. Part one's going to take a little bit longer because it's going to introduce the concept of a UART and how it works. So part two should be a little bit easier for that. The UART itself, I think it's worth mentioning, is actually just built into the micro USB connection on the Go board. So up until this point, we've been using that micro USB connection for powering the Go board and for programming the Go board. But there is a third use for it, and that is for talking to a computer. So that's kind of handy. That's one of the things that separates the Go board from other boards on the market, is that one micro USB connection is very versatile. You get 3 uses for the price of 1. So UARTs can be configured with a bunch of different configuration parameters. The first one is baud rate. This is the number of bits per second that gets sent down the line. So 9600 bits per second. Maybe you're from the days where 9600 baud meant something to you for dial-up modems. 56K modems, it's 56K bits per second. That's what baud rate represents. For the Go board project, we're going to be using a baud rate of 11.5200, which if you ever connected the Go board to your computer with the program that shipped with the Go board, that was the baud rate that I was using for that project. If you don't know what I'm talking about, just ignore it. Number of data bits, you can actually set 7 data bits. I've never seen 7 data bits before, but you can set that. I've always seen 8. Parity on or off. A parity bit is kind of like an error check bit, so it helps to see if there was an error in the communications. For this project, I'm just going to be turning parity off. And then stop bits, 0, 1, or 2. I'll talk about what that means. Flow control, I've never seen flow control used anywhere, so this is almost always going to be none. So you might be a little confused, but that's okay. This will make sense in about 2 seconds. Maybe here. UART data stream. So again, UART is a single wire from the computer to the Go board. Or, well, that's the particular example that we're using here. By the way, UART, you might have also heard this called like a COM port or an RS-232 interface or a serial port. Those all mean the same thing. When people use those, they kind of use them interchangeably. The right word is really UART. So when data gets sent from the computer, if you set it up for the configuration parameters that I was talking about, the first bit to come along is a start bit. The line, this is a 1 represented up here and a 0 represented down here. The line idles high for a UART, so it's driving a 1 to the line when it's idle. The start bit comes along, it's low for 1 bit period. So this bit period is set by the baud rate. So this, if the baud rate's slower, this is a longer bit period. If the baud rate's faster, this bit period shrinks. Start bit's low, and then we get 8 data bits sent LSB first. Least significant bit goes first, 0 through 7, and then the stop bit is high. So the receiver and the transmitter need to agree on the format of the data. So you got to set them up and say, okay, well, there's going to be 8 data bits, there's going to be a start bit, a stop bit, no parity bit, and once those two things agree, you can transmit the data. Now you'll notice there's no clock here, so it's up to you to find the middle of the data bits. So if you know, for example, that one bit is a microsecond wide, you need to sample it when a half of a microsecond has gone by to make sure that you're not sampling on the transitions. If you sample on the transitions of the data bits, you could have a situation where you're sampling the wrong data, and you don't want to do that. So the best way to guarantee getting good data is to sample the middle of the data bits. Okay? So that's it. That's going to be what this project is going to be doing. The Go board is going to be receiving data from the computer. Now, in order to receive data from the computer, we're actually going to be using a state machine. Perhaps if you're in a digital logic course, you've heard about state machines, but if you haven't, just a quick refresher. State machines are really useful to find a sequence of events or perform a sequence of actions. So do this, then do this, in this situation do this, after that's been done do this, after that's been done do this. And the bubbles on this diagram here represent individual states. So for example, I think a state machine is useful if you think of a good example, like for example, a passcode for a safe. So let's say you have a safe in your office and you want to open it. So you know that the passcode to open it is 479 on a keypad. And those need to be pushed in exactly that order, and if they're not pushed in that order, the safe won't open. Well, that speaks to a state machine implementation. And a state machine is represented, so let's take the situation here where you're in this idle state. You're in idle until you see the 4 get pushed on the keypad. If a 4 gets pushed, you transition, these lines are the transitions between states, into this check_1 state. If any other digit other than a 4 is pushed, then you just stay in idle, just looping from idle back into idle again. Once you're in check 1, there are 2 ways you can get out. You can get out this way or this way. Going out this way is when the next key pushed is equal to 7. If that's the case, then that's the right digit. You go into check 2. If anything other than 7 is pushed, you go back to idle. Once you're in check 2, you make sure that the last digit is 9, and then boom, the safe opens up and you're happy again. So again, the key sequence is 4, 7, 9. That opens the safe, and then you go back to this idle state. And that's a very simple example of how a state machine is used, but I did want to introduce this because it's very helpful if you design your UART receiver with a state machine. My examples that I show, the solutions that I show for VHDL and Verilog, both are going to use state machines. So here's the description. Let's get into the project. For this project, create a UART receiver that receives a byte from the computer and displays the byte received on the 7-segment displays built into the Go board. It's going to be a fun one. I like this project. The UART receiver should operate at 11.5-200 baud, 8 data bits, no parity bit, 1 stop bit, no flow control. So those are the UART settings that I was speaking to previously. And this is really what it's going to look like. Data is going to come in through the micro USB connection here. The Go board's going to see the serial data stream. It's going to convert the serial data stream from serial to parallel. So serial means that it's 1 bit at a time. Parallel means you can see the entire byte at a time. So that's what the job of the UART receiver is. And then it's going to take the output byte that it receives from the computer after it's been converted from serial to parallel, and it's going to send it right to that binary to 7-segment converter that we've used in the past. And there's actually going to be 2 of these, 1 for each digit of the display. So there's going to be a binary to 7-segment converter for the upper nibble, or the upper 4 bits, and a binary to 7-segment converter for the lower 4 bits. This is a fun project. Kind of ties a lot of concepts together, and it's definitely the most complicated one we've done so far. Is that the last slide? That's it. So I'm going to get started with the Verilog solution. I encourage you to give this one a shot, and if you get stuck, you can take a look at the Verilog solution that I threw together. If you want to do the VHDL, skip to that section. For the Verilog solution, I'm going to refer you to my EDA Playground environment. So go to edaplayground.com/x/figure 4, capital L, lowercase y, lowercase z. I will put this in the YouTube description as well, so you can go to this and take a look at my solution. On the right half is the low-level UART receiver. On the left half is the test bench for the receiver. Again, the test bench is going to exercise the functionality here and make sure that things are behaving correctly. The UART is, pretty complicated design, and it's definitely worth writing a quick test bench for to make sure that things are behaving correctly, because you're probably not going to get it right the first time. The inputs to the UART, only a couple inputs, the clock and the actual serial data stream coming from the computer. One output ORX DV, data valid, which is a single pulse, 1 clock cycle wide, and the actual byte that we receive from the computer. That's all we're trying to do, convert this serial data stream to a parallel byte. And in order to do that, we have, let's see, first of all, this parameter as well, I should talk about this quickly. This parameter you just set based on the frequency that we're using, divided by, the frequency of the clock on the Go board, which is 25 megahertz, divided by the frequency of the UART itself, or the baud rate of the UART. So for the Go board, it's a 25 megahertz clock. Divide that by 115200, and you get about 217 clocks per bit. 217 clock cycles for every bit of the UART data stream. The way this works in general, just to give you a quick refresher on the data stream, is the UART receiver will look for this falling edge of the start bit. So it sees this edge go low, and it says, okay, the UART line has gone low. I think that's the start bit. So it's going to count it's going to find the middle of the data bit. It's going to count halfway up to the middle. So in this case, it's going to count to 217 over 2, which in my head is 110, 113-ish, 113, 114, somewhere in there. It's going to count 113 clock cycles, and then it's going to check the start bit and see that it's low. Once it's low, then we know that, okay, we are in fact finding a UART data stream, and then it's going to count 217 more clock cycles to find the middle of each of the data bits. Once it gets to 217 clock cycles, it's going to reset the counter, sample the line. Then count 217 more clock cycles. Sample the line, reset the counter, count 217 more, etc., 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 until we have received all of the data bits. So let's look at what that code does. Let's see. So the state machine, the way I like to write state machines in Verilog is by defining these parameters and just giving them some constant, giving them some binary, something I set to them in binary. So for example, idle gets set to 0, RX state bit is 1. This is just giving a name giving an enumerated name to this particular binary value. Just a little easier to read the code. And there's some signals here. We're going to put this in a clocked always block, and we're going to be writing a case statement. So in the situation, we're testing the R_SM main, the main state machine. In the situation where the state machine is in idle, then we're going to say that we don't have any data valid. Keep the clock count set to 0, and we're on the 0th bit index. And we're going to stay in idle basically as long as we don't detect a start bit. As soon as we detect that start bit, then that's this falling edge here. We're going to get out of idle. So now we're going to go into the state called RX start bit. We're going to stay in RX start bit until we have found the middle of the bit, and that's what this if statement right here is looking for. So if the clock count is equal to clocks per bit minus 1 over 2, then we're in the middle. And here we just want to make sure that we are in fact still low. So if the input serial data stream is low, then bang, reset the counter, we're in the middle, so we're good, and then start receiving the data bits. So transition out of this state into another state. Then if for some reason the RX serial is not low, so maybe there was some glitch on the line, we're going to go back to idle and just wait for the next data byte to be received. Otherwise, so if we're not at this clock count value, then just stay in the state that we're in and increment the clock counter. So that's the nice thing about state machines. You can increment a counter a bunch of times, waiting for some situation to occur. In this case, we're waiting to find the middle of the start bit. Once we found the middle of the start bit, the counter gets reset again, and then we're looking for the data bits. Here, we're looking to see when the clock count is equal to clocks per bit minus 1. So when this is at its limit, basically, is what this is checking for. I'm sorry, if it's not at its limit, right? If it's less than clocks per bit minus 1, then we're just going to increment it and stay here. Otherwise, if it's in this else condition here, then it's going to be equal to clocks per bit minus 1. So that means that we are in the middle of a data bit. We don't know which data bit we're in the middle of, but it actually doesn't matter. We write code to make it agnostic. So this state is for all of the data bits. So when we get to the our clock count is equal to clocks per bit minus 1, bang, reset the counter back to 0, and then sample the line. That's what this line is doing here. So we've counted. We found the middle of the start bit, counted up to 217. Clear the counter, sample the data line. Clear the counter, sample the data line. And this is maybe a little confusing, but that's what this line is doing here. It's taking this register, RX byte, and the brackets indicate which bit position of RX byte we're actually going to be looking at. So this R bit index is going to count from 0 to 7, and that's going to keep track of which bit we're actually loading into this parallel byte. R bit index, so that's going to keep track of which index we're on, and as long as we're less than 7, then we're just going to increment it by 1, and then stay in the same state that we're in right now, RX data bits. So this will be set to 0 first. It's going to go to 1, 2, 3, 4, 5, 6, 7. Once it gets to 7, clear it, set it back to 0, and then we do need to receive the stop bit as well, just to make sure that everything is done. The stop bit's always going to be 1. And we're just going to wait for the stop bit to finish down on the line. And I go to a cleanup state once the stop bit has been received, stay there for a clock, and then go back to idle again. Cleanups, I use cleanup just to make sure everything is happy. We do need to assert the RX data valid pulse for 1 clock cycle right when the stop bit is received. So that gets set high once. And what that's going to do is that's just going to tell the module upstream that the data inside of the byte is actually valid. So the upstream module will not look at this byte here until it sees a pulse on this line here. Once the RTL code has been written, we do want to write some test bench code, make sure everything is working correctly. And the purpose of this test bench is just going to be to basically write a byte from the test bench to the receiver. So we're going to be instantiating the receiver here, generate a clock, drive that clock to the receiver, and then I created something new which you haven't seen yet, and that's called a task. Task in Verilog performs some action. It's kind of like a function in C, except the task doesn't have to return anything. So it just runs through. You basically call it, and it'll just execute the lines one at a time from top to bottom. Kind of nice. This task, you can read through what this does, but basically, its whole purpose is just to take some input data and serialize it, send it out to the receiver module. So the main testing, just wait for a clock cycle, call the task, and send some data. In this case, I just sent hex 37 to the receiver, and then wait and make sure that the output of the receiver, the W_RX byte, which is the output of the receiver, is in fact hex 37. If that's the case, display correct byte received, otherwise say incorrect byte received, and that's pretty much it. So when we run this, should be able to see EP wave opens up, but let's just take a look here. We do see, in fact, test passed, correct byte received. So that's a good sign. And I do recommend taking a look at EP wave and just adding the signals in the RX instantiation to your waveform viewer here. And this is nice. So we're seeing the clock is toggling, and here's the slow serial data stream, which represents the data from the test bench to the receiver. And it should be sending out, 37. So it'll send 0, 1, 1, 1, 0, 1, 1, 0, something like that. Where is it? Okay, yeah, this is the start bit that gets sent out first. So this is the start bit here. Then along comes the first one, the least significant bit, which is 7, but it's backwards, so it's 1, 1, 1, 0. So 1, 1, 1, 0. That's the 7. Then the 3 comes next, which is a 3 is 0, 1, 1, but backwards it's 1, 1, 0, 0. And then right here is the stop bit. So that is in fact what the receiver sees. It receives a 37 being received, and it asserts data valid out here, and we see 37 being received from the computer. So this is a very quick check. You might want to receive more than one byte on your test bench just to make sure everything's working correctly for the next byte. Make sure all your counters reset to the right thing. But this is a quick check that just seems to show that everything's working correctly for the UART receiver. So now that that's done, we still need to create the top level module, which is going to instantiate the receiver and drive the received data to the 7-segment display. So now I'll show you what that looks like. Alright, so for the top of the project here, we added this new input, IUART_RX. We have the output for segment 1, which is the upper digit, and we have the output for segment 2, which is the lower digit. And this is not too bad. So we have the UART receiver that we created. The output is W_RX byte. And all we're going to be doing is sending the upper nibble, so bits 7 down to 4. Again, the brackets are how you can address individual bits. So you can actually address bits 7 through 4 by using this nomenclature here. And that's going to be for the upper digit. And for the lower digit, it's going to be bits 3 down to 0. And you do need to invert the outputs based on the way the Go board is wired up. But that is it for the project. So I'm going to go ahead and build this and show you the results. First, I am going to do the VHDL section, so if you want to skip that, go right ahead. And then I will be building the results and showing you what it looks like on the Go board. Let's now look at the VHDL solution for the UART receiver. I have created an EDA playground environment at edaplayground.com/x/5v capital E lowercase h. I'll throw this on the YouTube description as well. This is the playground environment for the VHDL solution. On the right half here is the actual RTL that the UART receiver is being created with. And on the left half is the test bench code, the simulation code. This is throwaway code that we're just using to stimulate this stuff and make sure everything's working correctly. The entity for the UART receiver is relatively simple. We have a clock input, we have RX serial, which is the serial data stream being received from the computer. We have an ORXDV, which is a data valid pulse. This is going to be 1 clock cycle wide. And the purpose of this data valid pulse is so that the upstream module, the module that instantiates this receiver, knows when ORX byte has some valid data in it. So that's a handy thing. I use data valid pulses everywhere in my design. So anytime I see DV, I know, okay, it means that this data is actually, we can look at it, and it's 1 clock cycle wide. Handy thing. Also, there is one generic on this design, which does need to be set correctly. Generics, again, are basically constants that get set by the instantiating module. And this is just going to be set to the number of clocks in every single bit for the UART. And the way to set this up, the Go board uses a 25 megahertz clock. So take the frequency of the clock and divide that by the frequency of the UART, and that's what you need to set the generic to. For our example, 25 megahertz divided by 115200, the baud rate of the UART is going to be equal to 217. So there's going to be 217 clock cycles of the 25 megahertz clock for every bit received on the UART. So this width of time from the beginning of the start bit to the end of the start bit is going to be 217 25 megahertz clock cycles. And we are going to be using a state machine, and the best way to create state machines in VHDL is to create your own enumerated type. That's what this is called here. This line is creating an enumerated type. The type that we're creating, I just called it T_SM main, and then you give it the names of all the states that you're going to be using. Idle, start bits, data bits, stop bit, and a cleanup state. Then when you create the actual signal that is your state machine, instead of giving it a type like standard logic or integer, give it the type that you created previously and set it to idle. So it's going to start up in an idle state. Okay, there's some counters and things here, but let's look down at the actual sequential process that controls the state machine. So we start off in an idle state, and we're just gonna chill in this idle state until a start bit is detected. So if we see the input RX serial line go low, again, remember that the idle state, it idles high. So when it's going low, that means something's happening on the line. And it's going to be a start bit. So we're going to go into the receive start bit state. Once that happens, we're going to count to G clocks per bit minus 1 divided by 2. And what that's going to be doing is it's going to be aligning us to the middle of the start bit. And once we're in the middle of the start bit, we're going to sample the line again. And that's going to make sure, we just want to make sure that it's still low. So it might happen, there could be a situation in which the UART could glitch and trick the state machine into thinking, oh, there's a data bit coming because I saw the line go low, but maybe it goes back high again and it's really just a glitch on the line. So we want to make sure that once we're in the middle of the start bit that we're still low and that we're actually going to be receiving real data. So what that does is that's basically this transition here, this look for the falling edge. We count off to G clocks per bit minus 1 over 2, which is going to be this point in time here. Sample the line again. Once it's low, we say, okay, we're definitely receiving some data, so let's get ready for it. And that's what that does so far. And then we're going to go into this RX data bits state once we know that we're ready to go. Now we're going to count to G clocks per bit minus 1 and then sample the data again. So that's going to count up from 0 to 216, so 217 clock cycles altogether. Once we get to the middle of the next data bit, that is represented by this else condition here. And all we do is do two things. We reset the clock and sample the data that's on the line. So this is something probably a little bit new, but RX byte is going to contain the parallel received data in a byte form. And if you put a parentheses like this, then what that's actually doing is that's actually indexing a particular bit of this byte. And bit index is going to count. It's going to be an integer that counts from 0 up to 7. It starts off at 0. So the very first thing we do, our bit index is going to be set to 0, so we're going to assign bit 0 of the byte to IRX serial. Then it's going to increment bit index by 1 and do the same thing again. Count up to 217, sample the line, increment the bit index by 1, count to 217, sample the line. And that'll happen until bit index is equal to 7. When bit index is equal to 7, that means that all the bits have been received. And actually, this is actually a typo. Check if we have not sent out. Received. Check if we have received all bits. That's what we're looking for. And once we've received all the bits, then we are going into the stop bit state. And we're just going to receive a stop bit. We're not going to do anything with the stop bit, but we're just going to count for G clocks per bit minus 1 again, wait for the stop bit to finish. When the stop bit finishes, we can assert the RX data valid pulse for 1 clock cycle. I like to go to a cleanup state just to make sure everything is happy again. Set RX data valid back to 0, and then we're gonna go back to idle, and we're gonna sit in idle and wait for the next serial data stream to come along. So I think that should work, but let's just make sure that it does. So let's write a little test bench that just stimulates this guy. So we're going to use a 25 megahertz clock. Going to set clocks per bit to the 217 value, which is the 115200 baud rate with the 25 megahertz clock on the go board. And this is a new keyword in VHDL that we haven't yet talked about, which is procedure. And a procedure is, I'm trying to think if I've seen them in synthesizable code before. I haven't. I don't think I've ever seen a procedure in synthesizable code. I think you can synthesize procedures. You definitely can't synthesize this procedure because it has this wait condition in it. Most of the time for synthesizable VHDL code, I see functions more than procedures. But I believe you can write a procedure as well. Either way, I most of the time use procedures for test bench code. And all it does is it performs a sequence of events from after the begin statement to the end statement, in sequence. So send the start bit, wait for C bit periods, wait for some amount of time, and then send the data byte in this loop. Oh, here's a for loop. Look at that. You can use for loops in test bench code, and they do behave very similarly to how they would behave in C, where they loop through this. They loop through this sequence of commands here, including this wait statement. You can have this variable II, which you can increment. So this is how a for loop might be used. Again, never use a for loop on this half of the screen in synthesizable code because it doesn't do this. This is, well, maybe someday we'll talk about how for loops work in synthesizable code, but not like this. The procedure then sends the stop bit, and we're done. Okay, so the receiver is going to be instantiated here. We have a clock being set up, and then here's the actual meat of the test bench right here. It's inside of a process, a not sequential process with no sensitivity list, but it just runs from top to bottom. Very first thing, wait until rising edge clock, then we're going to do this statement, which is calling the procedure that we created previously, and it's going to write X37. X with quotes around it means a hexadecimal number. So we're going to be passing the 37 to this procedure. And we're also going to be passing our RX serial, which is the serial line from the test bench to the RTL code that we created previously. And that's going to allow that procedure to drive that line. This is the way in VHDL you have to do it. If you want a procedure to drive a signal, you have to give it the signal to drive. It's kind of annoying. Verilog's a little more flexible than VHDL in that respect. Okay, wait until rising edge clock, and then once the procedure is done, we just want to check the data that's on W underscore RX byte and make sure that it's 37, which is what we sent out. And if it is, we say, throw it on this report, which says, yep, we're good. Otherwise, say bad, and we can say test is complete. So let's run it, see what happens. Did it finish? No. Okay. EP wave opens up, but let's just take a look at the console output here. Execution note, test pass, correct byte received, yay! And then it says a failure test complete. It's because I threw down this assert false severity failure. That's why that says failure. It was a pass, it was a success, but let's take a look at the EP wave just to confirm that it was successful. UART receiver, let's add those. Okay, so it looks like we're doing some good stuff here. IRX serial, that's the UART serial data stream. It started high at the beginning of the simulation, went low for one baud rate period, one UART bit period, I should say. That's the start bit. That looks good. Then we received the 7 first in the 37, but so a 7 is 0, 1, 1, 1, but the data gets sent least significant bit to most significant bit, so it gets sent 1, 1, 1, 0. So this is a 7, that looks good. The next one is a 3, which is 0, 0, 1, 1, but again, it gets sent least significant bit first, so it's 1, 1, 0, 0. And then here's our stop bit out here. So that looks good. It looks like the transmitter is sending the right thing, and the receiver sees that as well. So the bit index is counting up. We see it count from 0 to 7, resetting back to 0 again. The clock is counting up, and the RX byte is in fact changing as we assign the serial data stream to it. But in the end, we do get 37 out here, so that looks good. And then we have the RX data valid pulse for 1 clock cycle out here, which says that we're done and data is valid. So that should confirm that the low-level receiver is working correctly, but we still need to create the top-level module, which is going to take the output of the receiver and drive the binary to 7 segments. So let's look at that code now. Okay, here's the top for the VHDL section. We have our clock, we have our RX data from the computer, we have segment 1, which is the upper digit, segment 2, which is the lower digit. We're going to instantiate the UART receiver, set it to 217, and give it the UART data from the computer. And out of that we're just going to have this W_RX byte signal, which the upper nibble, or the upper 4 bits, we're going to give to the upper digit, 7 down to 4. And the lower nibble, which is 3 down to 0, we're going to give to the lower digit of the 7-segment display. And that's it. We do need to invert the outputs because of the way the Go board is wired up, but this should be everything. So now the Go board will be displaying the data transmitted from the computer onto the 2-digit 7-segment display. So let's program the Go board and take a look at the results. Okay, the Go board has been programmed, the code is running, and I have opened up a new program here called Teraterm, T-E-R-A-T-E-R-M. I would recommend Googling that and downloading this program. It's a terminal emulator. It's good. It's free. It's open source. It's definitely my favorite one. Once you download it, this is going to be what you type into. It kind of looks like an old MS-DOS window or Linux terminal or something. And this is what you're going to type into to send data to the Go board. And in order to do that, you do need to connect to the Go board. So the best way to do that is click on Setup, Serial Port, and connect on. Mine is on COM5, but you can just figure that out by trial and error. COM5, 115200, 8, none, 1, none. These are the settings that we looked at previously. Click OK. And now when I type in here, nothing is happening on the Teraterm window, but you'll notice on the Go board that the 7-segment display is changing. It's a little hard to see due to the lighting in this room, but that's 31, that's 32, there we go, 33, 34, 35, let's see what else we got. Ooh, 6E, 6.2, 20, 6F. Now my question to you is, why is this happening? Why aren't you seeing, well, what do you expect to be seeing? Do you expect to see a G? Well, you can't really draw a G on this display. So what you're going to be seeing is you're going to be seeing the ASCII hex encoding of each key that I press on the keyboard. And if you go to like a if you Google ASCII table, you'll see the full ASCII hex encoding table. But I know for a 1, for example, is 31, a 2 is 32, a 3 is 33. Let's see what else. A P is 70, an O is 6F. What this is doing is it's taking the keyboard presses and encoding them into ASCII and displaying the ASCII value on the 7-segment display. So this is fun. You get to learn about how ASCII works for this project, which is pretty neat. So everything is working correctly. You're receiving the ASCII data. You're displaying it on the Go board. So now you have successfully designed the UART receiver. Congratulations. The next project is going to be creating the UART transmitter, which is going to close the loop. So now we're going to have a receiver and a transmitter. And so let's get started with that now.